there are a few important points that we need to discuss, and that you will find in the description section of the controller datasheet. This will give you an exposure to how to look into the datasheets as well as learn about the controller. So I have moved away, at least for this segment, this part of the segment, I have moved away from the slides, and I have directly come to the datasheet to chapter 2. So the chapter 2 is a description of the controller that we are going to use, that is STM32F411. So the datasheet will vary from controller to controller. If you have STM32F407xC, then the datasheet will be different for that controller, and so on and so forth. Now, the STM32F411 devices are based on the high performance ARM Cortex-M4 32-bit RISC core that we know, and the frequency can go up to 100 megahertz for this controller, though we are going to set it for 84 megahertz operation. The Cortex-M4 core features a floating point unit, which we talked about, single precision, which supports ARM single precision data processing instructions and data type. It also implements a full set of DSP instructions and a memory protection unit, which enhances application security. Now, this is something that you will not find in, say, a 8-bit controller. For example, you can it actually has DSP instructions, so you can perform DSP operations on this particular controller also. Not extremely powerful DSP applications or extremely heavy DSP applications, but audio processing and the likes, or say signal smoothing and things like that, can be easily implemented. For example, you can implement for lower frequencies, you can implement different kinds of filters with this controller. So that is a great capability that this controller has. Now, it belongs to the STM32 dynamic efficiency product line, with products combining power, efficiency, performance, and integration, while adding a new innovative feature called batch acquisition mode, called BAM, allowing to save even more power. So we'll not get into the BAM or batch acquisition mode as such, but it's good to know. And it incorporates high-speed embedded memories up to 512 KB of flash memory and 128 KB of SRAM, and an extensive range of enhanced IOs and peripherals connected to the two APB buses. So we will see what these buses are. And the 2 AHB bus and a 32-bit multi-AHB bus matrix. So we saw the bus matrix a little while ago, and we will have a look at these buses also. Now, all devices offer one 12-bit analog to digital converter, a low power real-time clock, 6 general purpose 16-bit timers, including one pulse width modulation timer for motor control, 2 general purpose 32-bit timers. They also feature standard and advanced communication interfaces. So it has up to 3 I2C interfaces, 5 SPIs, serial peripheral interfaces, 5 I2S, out of which 2 are full duplex. Okay? To achieve audio class accuracy, the I2S peripherals can be clocked via a dedicated internal audio PLL via an external clock to allow synchronization. 3 UARTs, that is UARTs serial ports, and SDIO interface, and USB 2.0 OTG full speed interface. So it provides you all of this, the controller that we are working on. So here you can get some information on the temperature, and if you go further down this down the data sheet, it will give you a lot more information about the controller characteristics. Okay, so read it at your free time. It's interesting. So embedded systems is not just coding on the processor. It is also having an in-depth knowledge about how the processor functions, the architecture of the processor, and the hardware that the processor needs to control. So it is an interesting field where you need to think differently than enterprise applications. These features make the STM32F411xC microcontrollers suitable for a wide range of applications. So what are the applications that it supports? you can do motor drive application control, medical equipments, industrial applications, PLC inverters, circuit breakers. We saw some of them in the pictures to begin with: printers and scanners, alarm systems, video intercom, HVAC, home audio appliances, mobile phone sensor hubs, and so on. So lots of use for this controller. Now it's just a table which talks about the peripherals once again. So STM32F411, you have XC and the XE variant. So the XC variant has 256 KB of flash. XE variant has 512 KB of flash. RAM is 128 KB. General purpose timers are 7 across both the variants. Advanced control timers it has 1 advanced control timers, 5 SPI, 3 I2C, 3 USART, 1 SDIO, and then 1 USB OTGFS. So this is what we saw previously, and it has been given in a tabular format. How many GPIOs it has. So it can have different GPIOs depending on different variants of the processor. For example, how many pins the processor has. So again, then that processor will have different form factors. So it can have 36 GPIOs, 50, 81, and then 36, 50, 81 again for each variant. Okay. And then number of channels for each variant, again 10 and 16, 10 and 16. Okay. And then you have maximum CPU frequency goes up to 100 megahertz right across. Operating voltage is 1.7 to 3.6 volts. This is important when you are working with IOs basically. So 3.6 volts is the upper limit for any analog. If you are working on ADC, you should not exceed this voltage when you are feeding analog signals to the processor. Digital signals is a different story because those are 5 volt tolerant pins, and we shall see that later. Operating temperatures, ambient temperature, it can operate from minus 42 plus 85 degrees centigrade, or minus 42 plus 105 degrees centigrade, or minus 42 plus 125 degrees centigrade. Junction temperature is minus 42, 130 degrees centigrade. And the packages are different. So whatever you saw, as we were saying, the packages, depending on these, so these divisions that you see are different packages that you have: WLCSP, UQFPN, LQFP, okay, UFPGA, LQFP, so on and so forth. So depending on these packages, you have these pin counts. Now it talks about compatibility of this processor with different processor series. Like if you want to change the processor on your particular hardware, so you have, say you have a 100 pin processor package, and you want to upgrade or you want to change the processor. So this talks about if you are changing the particular controller, which are the controllers that are compatible, and what else you need to do for on the hardware or on the PCB to use the other processor. So that's what it talks about here. You can have a look. So here it talks about all the compatibility information, and now we come to an interesting part of the controller, and that is the entire architecture diagram of the STM32F411xC or XE. So this is the block diagram. So let's make the diagram even bigger and go through the different sections of the diagram. Okay. So it looks quite daunting to begin. So we'll go through this diagram section by section, and we'll try to understand what is where. Now this is what we had already spoken about, though it looks slightly different. This is the Cortex-M4 core. You have the JTAG interface, ETM interface, okay, memory protection unit, NVIC. You have the data bus, instruction bus, S bus, and this is your controller. And then we spoke about the bus matrix. So it all goes into the bus matrix. From the bus matrix again, so we saw a rough diagram of the bus matrix. So here this is more detailed. It goes into the accelerator cache, and then it goes into the 512 KB or whatever flash size you have, and then it goes into the 128 KB SRAM. So these are the, so directly from the ARM Cortex-M4, we have through the bus you have an interface to these memories, different memory segments. Now from the bus matrix, we have different kinds of buses now going out. One bus is called the AHB2 bus, and this bus is the max speed on this bus is 100 megahertz, and it goes out to the USB OTG. Okay, so this is your USB unit, and this AHB2 bus has a maximum frequency of 100 megahertz. You have, so, and this is the AHB2 bus. There is another bus that is coming out of the flash in gray, and we'll see where it goes. So this is the AHB1 bus, and we'll see where it goes. The AHB1 bus goes to these two DMA channels, and then it goes to the different ports, different GPIO ports, and then it comes down to AHB to APB bridge. Okay, so AHB bus is the basic bus that we have, the main bus. Besides AHB2, AHB2 is only for the USB. So AHB bus, and from AHB bus there is two more buses emerge. So we have all the GPIOs connected to the AHB. So these GPIOs are quite high speed, and this AHB bus, AHB1 bus rather, it is connected to the backup register, RTC, and so on. So this AHB bus, as you can see, this connects to the clock unit, this connects to the CRC unit and the GPIO, and then it comes and splits up into APB2 and APB1 bus. So buses are nothing but interconnects, as we spoke of, and then there are other parts of the controller, like you have this power management, you have supply supervision, you have VDDA, and so on and so forth. So these are different reset and clock control, RCC units, and so on and so forth. Okay, so these are different units of the controller. Once the AHB bus is broken up into two buses, APB2 and APB1, so if we'll have a look at the APB1, we'll see that external interrupt wake up is DIO, MMC, timer 1, PWM, timer 9, timer 10, timer 11, USART 1 and USART 6, SPI, SPI 4, temperature sensor. Everything is connected to this APB2 bus, whose maximum frequency can go up to 100 megahertz. And this side of the bus, this bridge from AHB to APB1, again has the power interface. We saw that and again one unit can be connected to multiple buses. For example, as you can see, the AHB1 bus is connected to the LS here. Again, the APB1 bus is also connected to. So these are just data paths. Okay, so data is flowing over these buses. Data and control is flowing over these buses. That's all. So this is just like looking at a map of the controller, how things are laid out. So if you consider this as a map, and where the different components reside, it will become easy for you. So again, you have, for the APB1 bus, you have different timers, and the maximum frequency of APB1 again can go up to 50 megahertz. It cannot go above 50 megahertz. So you have the timer 2, timer 3, timer 4, timer 5. USART 2 is connected to this bus. You have SP2, I2S, SP3, I2S3, I2C, I2C2, and so on and so forth. SCL, SDA, all of them are connected to this particular bus, and the watchdog is also on this bus. Okay. And one more thing is, the timers are connected to the APB2 clock from timer clock up to 100 megahertz, while the timers connected to APB1 are also clocked to 100 megahertz. So timers are 100 megahertz, but the but this bus has a maximum frequency of 50 megahertz. Here the maximum frequency is 100 megahertz. Okay. So the timers might be running at 100 megahertz, but then the bus data speed on the bus is the maximum it can hit is 50 megahertz, as it is written here. Now, so this is what the inside of the processor looks like. Now, if you open up the processor and try to look at the die, it will not look like this, but this is put in a more human understandable form. So this is what we are going to work on. So all our program and RCC clock control, we will be working on these registers. So there are registers in the clock control registers, clock control area. Then you have different different peripherals like USART and timers and all that, which will have their own respective registers, which we'll need to configure to enable these. So all of that we are going to see. Now, for example, there's something interesting. For example, all these devices, whatever you have, timers and GPIO, I2S. For example, if you have I2S, the I2S has to come out through the ports only, right? So even if you configure, say, a particular peripheral here, you have to configure the respective port that the peripheral is supposed to be connected to. So every pin has an alternate function. So you have to configure the peripheral here, and you have to configure the port so that that data actually has to flow out through this peripheral. Okay. So, sorry, that data has to flow out through these ports, not peripherals, through the ports. So all of that has to be done in code, in the sense configuring the peripherals and configuring the ports, configuring them to be output ports and input ports. And as you can see, it looks more difficult, or it looks more complicated than a 8-bit or 16-bit controller. And that is the reason why you need to be with a lot of processing power comes a lot of complexity. So of course it is not simple, it is more difficult than that, but then we'll go slowly through the course, and we will try to understand a few components. We will try to understand, then we'll talk about SysTick and so on and so forth. And by the end of the course, I hope that it will build a solid foundation for you to go further and build more complex projects on this class of controllers. Not only STM32F411, but other classes of Cortex-M controllers as well. Now, the Cortex-M4 with floating point unit core also contains hardware extensions for advanced debugging features. Now, the debug extensions allow the core to be stopped either on a given instruction fetch, that is breakpoint, or a data access, that is watch point. When stopped, the core's internal state and the system's external state may be examined. So you can stop the processor, and then you can examine the state of the registers, the state of the memory, and so on. And we are going to do that going forward when we in other sections, when we are investigating say we are in the interrupt, when we are in the interrupt section, or we are in the other sections, we will be actually using the debugging feature heavily. Once examination is complete, the core and the system may be restored and program execution resumed. Two interfaces for debug are available. One is a serial wire and another one is a JTAG debug port. And the ST-Link version 2 programming and debugging tool or hardware is integrated into the STM32F411 discovery board. So there is another chip that you have on board besides the chip that we program on, which will take care of the debugging for us. So we don't need a costly external debugger for trying out the debug feature, and that is what we are going to use. Now, this is a general diagram of the Cortex-M4 peripherals that you can have, and we saw that. That is, you can have DMAs and GPIOs, EEPROM, watchdog timers, hyper. This is general. This is not for this particular processor, but this is just a diagram, overall diagram, and I've just segregated it into different peripheral classes. For example, you have system peripherals, which is like DMA, GPIO, PROM, watchdog timers, hibernation module, general purpose timers. Serial peripherals could be USB, SPI, UART, I2C, CAN. This particular processor that we are studying does not have a CAN interface. And then analog peripherals like analog comparators and ADC channels, and motor control peripherals like PWM and QUI and so on. Now this is an important slide. This talks about the Cortex-M4 register bank. That is the registers within the Cortex-M4 core. So this is common across all Cortex-M4 controllers, right across for all vendors. So this does not have any, this particular register architecture is going to be the same across all Cortex. So any code that you write for one Cortex-M4 which has to do with these registers can be safely ported to other processors from different vendors. This is quite standard actually. So now, the registers are within the processor chip. A register stores 32-bit value. So since this is a 32-bit architecture, we talked about this. And STM32F411 has R0 to R12, which is 13 general purpose registers. So registers are a part of all controllers. If you have 8-bit or 16-bit controller, there will be registers in the code which are used for programming. So eventually all your code, whatever code you write, needs to come to the registers to be processed. So R13 is the stack pointer, shadow of MSP and PSP. R14 is the link register, R15 is the program counter, and there are special registers like XPSR, base pry, and primask, etc. Now these are general purpose registers which are called low registers, that is R0 to R8. And then you have high registers which are general purpose, R9 to R12, and then there are special registers like stack pointer, link register, and program counter. Now, the link register holds the address of the program counter when there is a so the program counter holds the address of the next instruction to what is being executed. So we'll come to a slide where the program counter is shown in more detail. Link register is when you have, say, you are executing a subroutine and then you jump to another subroutine. So when the jump happens, there is a assembly instruction called branch and link. So when you do that, wherever you jumped from in that particular caller function, that the next address to that is stored in the link register. So the link register, when you are actually coming back from this function to the main function, it loads back that link register content into the program counter so that the execution can continue from where it left off, or one instruction after where it left off. And then again, the stack pointer, there are two stack pointers which are called shadow of main stack pointer or PSP. That is, there are two, you can maintain two stacks. One is the main stack, another one is the process stack in the ARM processor. So in our course, we will be only using the main stack pointer. Process stack pointer will not be used. This is used when you are working on real-time operating systems. So the processes are going to use the process stack pointer. And so these two stack pointers, if they have different addresses, so if you in your memory location, you will have, say, two different stack areas. Depending on which stack pointer you load into R13, based on these two, your stack is going to be accessed from that area. So for, say, the main stack pointer could have its stack in one area of memory, and the process stack pointer could have a separate stack. So all the functions in the processes are going to access a different stack. So this is the Cortex-M4 register bank. But since this course is mostly in C and very little assembly, you don't really need to worry about what is happening with these registers. In the sense, you don't need to take care of writing into the registers and writing instructions which deal with these registers. Yeah, so that is going to be done by your compiler anyway, but it is very important to know what is really going on. Hence, you need to know about the registers. Now, you would have needed a much more in-depth knowledge about how to work with the registers if you are programming in assembly. So then it's an absolute imperative that you learn about the registers. Now, there are some special registers which this is again common to all Cortex-M4 cores. That is, you have APSRs, IPSRs, and EPSRs, different registers, and these registers again can be combined and called and used. For example, there could be a combination of APSR, IPSR, and EPSR, and so on and so forth. So these are called program status registers. So let us now go back to the data sheets and reference manuals and try to find out where these registers are. And from there, we will see what these registers contain and what they do. So let us guess where these registers could be. Now, since this is core Cortex-M, let us look into the programming manual for the Cortex-M for STM32. Let's see if we can find the registers here. Because as we said that core is common between all the processors, and we are right, these registers are to be found here. Now, these registers are called program status register, and it contains the application program status register, which is the APSR, interrupt program status register, which is the IPSR, and execution program status register, which is the EPSR. Now, as I said, you are also learning how to navigate the data sheets and the programming and the other manuals. So I'm deviating from the slides here and there so that you get an exposure to these data sheets. Now you have the APSR, IPSR, and EPSR, and then PSR is again, it's a combination of three. So access the registers individually or as a combination of any 2 or 3 registers using the register name as an argument to the MSR or MRS instructions. So MSR, MRS instructions are assembly instructions, and we will not be using these instructions in our course anyway, but it is good to know. So read all the registers using PSR and MRS instruction. Write to the APSR NZCV Q bits using APSR and the MSR instruction and so on. Okay. So register combinations is PSR is a combination of APSR, EPSR, and IPSR. So if you write an assembly code with PSR here, it will combine all the 3 registers and access it like this. Okay. So ICI and IT, these bits you won't see come here, but all the combination of 3 register, all the bits mostly are seen here. It is as if all these 3 registers have got superimposed on one another. Then IEPSR is again EPSR and IPSR, combination of this. IAPSR is APSR and IPSR. EAPSR is APSR and EPSR. So this is nothing but different combinations of registers that you can call, and you can superpose them so that, for example, you want to do superpose APSR and IPSR. So you write assembly using IAPSR, and the ISA or instruction set architecture will know that you are referring to this particular register. So when it accesses these 2 registers combined, then it will be one block with the ISR number superposed on this particular register. So it will be like all of this with the ISR number. So if you superpose all the 3 registers, whatever you see will be as one register. Now, application program status register, let us go through the fields of these registers. For example, APSR, IPSR, and EPSR. So for APSR, you have different fields. N is a negative or less than flag. So APSR contains current state of the condition flags from the previous instruction. So if you have worked on assembly coding, you would know that different instructions would raise, or different instructions would set or reset different flags, and this is the place where all of that is done. For example, you have a negative, less than flag, zero flag, carry flag, overflow flag, DSP overflow and saturation flags, sticky saturation flag, so on and so forth. Greater than or equal to flags, okay, GE 0 to 3. Okay. Then you have interrupt program status register, which actually gives you the ISR number that is running. Okay, so it will tell you what ISR is actually running at that point. So NMI, hard fault, memory management fault, bus fault, so on and so forth. So all the interrupts are going to be numbers. Whatever interrupt you have is going to be visible. So if you want to check what interrupt is running currently, this is the register to look into, IPSR. And then you have EPSR, or it contains the thumb state bit and the execution state bits of either the if then instruction or interruptible, so ICI instruction field. Okay, so the fields are like this, that is ICI interruptible continual instruction bits, and IT indicates the execution state bits of the IT instruction. And then this says that the thumb state bit, whether it's working in the thumb state or the arm state. So this is another. So attempts to read the EPSR directly through application software using MSR instruction always return 0. Attempts to write to the EPSR using the MSR instruction in application software are ignored. Fault handlers can examine EPSR values in the stacked PSR to indicate the operation that is at fault. So EPSR cannot be accessed directly, it has to be accessed through the PSR, that is when it's clubbed together, superposed. So here, if all of them are superposed together, that is when you can see this. So ICNT, whatever this bit ICINT comes here, so you can read it from the PSR once it's superposed. You call the PSR and then you can read it, but you cannot read this individually. So that's about these special registers. Now, not only are the registers that you saw available, there are other registers also which belong to the floating point unit, and there are 32 registers which belong to the floating point unit, and each of them again are of 32-bit width, and these two registers can again be combined together, and they are called D0, D1, D2, D3, and so on. And floating point status and control register is called FPSCR. So when you are doing floating point data processing, we shall see that later. When you are doing floating point data processing, your different set of registers are used for floating point, and those are these registers. Say you declare a variable, say float something. Say you declare, say float equal to 2.35. The moment you do this value, or not till now. So if you do float num 2.35, it goes somewhere. It goes and sits on the stack. But then the moment you do a float num2 equal to 5.66, and then the moment you do say num2 into num, the moment you try to do some operations on these two values, these registers start getting used. Okay, so you can then at that point these floating point registers will come into action. So that is the use of the floating point registers. Then you have special registers called pry mask, fault mask, base pry, and control registers. We'll not talk much about them here because we deal with these registers extensively later in the interrupt chapter. But then these are interrupts and exception masking registers. Okay. Now this is the Cortex-M4 memory map. It is a general memory map of the Cortex-M4 core. and where your different sections are supposed to be. Now, say for our controller, all of this is not going to be occupied, of course. For example, the code section itself is half a GB, that is the area of between in which the vendor is free to choose any area within this code section. For example, in the case of TI, we saw that you have your flash memory starting from this address. In the case of STM32, it starts from, okay, both are hex. So TI is, say, the memory is here. For ST, it is somewhere here, the flash from where it starts. But both of them are okay because they still fall in the designated area, which still satisfied the Cortex-M4 or Cortex memory map compliance. Okay. Now then you have the SRAM, again 0.5 GB of space, of which we either use 128 KB, 256 KB and so on. So, but that area is between 2 with 7 zeros and 3 with 7 Fs. So no matter, whenever you have an SRAM, it has to be within this area. The different vendors can have start from different area and end in a different area depending on their size. For example, in the case of ST, it starts from here and it goes up to whatever size it wants. Say if it's 128 KB, then it's this one plus 128 KB. Then you have the peripherals, again 0.5 GB. Not all 0.5 GB is going to be used. It is just a small fraction of this. And then of course this peripheral addresses could be different for different controllers and from different vendors and so on. But most of their addresses will start from 4. Then you have the external RAM. If you are, we don't have any external RAM, but if you have an external RAM, this is the memory area that you can access. Then you have the external peripherals. It starts from A with 7 zeros and D, F, 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 F. So this is the external peripheral. The memory space is 1 GB. Okay, but then it's much lesser. So within this area, vendors are allowed to place their peripherals. And then this is the private peripheral bus, and then the system memory. Okay. So private peripherals including built-in interrupt, NVIC and debug components, everything falls in here. Okay. The private peripheral buses memory range from, again, E all 7 zeros to E00FFFFF. Yes, the private, and SCB buses memory range from E000, to E000, EFFF within the PPB. So within the PPB, again, you have the SCB. So this is for the system, NVIC and private peripherals and everything. And this is your memory space for the external peripherals. And it goes on like this. So this is a 4 GB space, but then this is not fully used. There are gaps in the memory, of course. There are huge gaps basically where you cannot access. And if you try to access those memory areas, suppose in your code, you're going to get some hard fault or memory fault. So you're going to get a mem fault. Okay. So mem fault, there'll be some interrupts, hard fault interrupts raised, saying that you're accessing an area which is not there, even though it falls in this memory map, but then it's not available. So if you hit that area somehow, you're going to not get anything in return, and the processor is going to fault.